This is ELEC142 problem sheet 6 on filters, and this is how to answer question 2. So question 2 is practically identical in the questions you need to answer to question 1. It's just this time we've got an RC filter, so we have a resistor and a capacitor instead of a resistor and an inductor. So you're asked to answer a series of questions where we're going to analyse the filter basically. So first up we're asked, is this filter a low or a high pass filter? So let's look at the positions of our components, and that's how we can work it out. So we've got the resistor here and the capacitor on the vertical. So let's look at our filter sheet and work out which one it is. So resistor and a capacitor. This is this configuration here. So we can see that this filter is actually a low pass filter. That's how we characterise it. If you want a bit more detail of why this is the case, please just go back through the lecture notes where we talked about the behaviour of the capacitor as the frequency changed, and that's how we know what this does. So the answer is that it's a low pass filter. Where's that gone? There we go. I've just redrawn it here. It's a low pass filter. Next up, we're asked to find the cutoff frequency. So the cutoff frequency, omega naught. Again, we're going to look at our filter sheet. So what we can see here is that for any filter which contains a capacitor and a resistor, the cutoff frequency omega naught is equal to 1 over RC. It doesn't matter if it's a low pass or a high pass configuration, because it's the position of the components that determines that. Look how these are in the opposite places for the low and the high pass filters, but the cutoff frequency will remain the same. So it's just 1 over RC. So let's put some values in and find that out. So it's 1 over RC, so it's 1 over 16, that's our resistor value, times 10 times 10 to the minus 6, because it's 10 microfarads. And what that gives us is an answer of 6,250 radians per second. And that's the answer you're given. I've just added a note here, really. You can convert this into hertz, because omega is equal to 2 pi f, and this gives us a cutoff frequency of approximately 1 kilohertz. So that's why it's just a guide for what we're using, really. It's just for your information. So that was part B. Part C, we're asked to redraw the circuit as a potential divider, and as I said before, this is just guiding you through the steps to characterise it. So how did we do this? Well, this is the answer. You need to recognise that V in passes through the resistor and the capacitor, whereas V out is only across the capacitor. And if you can take this step by going from this form of the circuit to this form of the circuit, you're really on the way to understanding what's going on. The other thing I've done in here is I've just replaced the capacitor. Instead of 10 microfarads, I've replaced this with minus J over omega C. And before, when I've used capacitors, I've said it's minus J 1 over omega C. It's exactly the same, it's just a slightly different way of presenting it, and in case of filters, it makes it the mathematical manipulation of the complex voltage transfer function a little bit simpler, but it's exactly the same. So next up, part D, calculate the complex voltage transfer function Hj omega. So the way we do that is we need to look at the output over the input. We can recognise this by the potential divider form, and we can see that the output is minus J over omega C all over R minus J over omega C. It's R plus, but this is a minus, so we've just cancelled that positive symbol. So that's what we've got here. What we need to do next is divide through by minus J over omega C, because we want to end up with 1 on the top. So we always divide through by whatever is on the numerator. And we get this expression, so it's 1 over R over minus J over omega C plus 1, which we can rearrange and say that's equal to 1 over 1 plus J R omega C. I went through why this is the case in the lecture notes. We can manipulate it, so you should be able to see that the omega C comes up to the top immediately, and if we just replace the position of the J, it becomes positive because it's a change of phase, essentially. And this then simplifies to being 1 over 1 plus J omega over omega naught, and the reason of that is because omega naught is equal to 1 over RC. So we can simplify it further. So that's the final answer, and this is showing you the level of detail you need to show. You can skip this particular part if you want, that's not required, but you need to see that it can go from potential divider form into this type of form. I'd recommend you show this as well, because if you make a mistake, it's going to be easier for me to follow it through to award you marks, really. So next up, we're going to look at the response of the circuit at different frequencies. So that's what these next three parts of the question are looking at. We're going to look at low frequency, where omega tends to 0. Then we're going to look at high frequencies, where we can assume omega tends to infinity. And then we're going to look at the cutoff frequency response. So let's do that now. So at low frequency, omega tends to 0. I've stated what I'm working with. So what we do is we rewrite the complex voltage transfer function, and this time where we see omega, we replace it with 0, because that's what we're doing. So we put in 0 there. What this then becomes on the next step is it becomes 1 at an angle of 0 degrees over 1 plus j naught, which means there's no j. There's no j. J is 0. So we can rewrite this as 1 at an angle of 0 degrees over 1 at an angle of 0 degrees, which remains the same. So because hj omega is a polar form, what we can see is that this is the amplitude response and this is the phase response. It's either side of this angle sign. So we're just going to summarise that and say the amplitude response is 1, which means there's no attenuation, and the phase response is 0, so there's no distortion. And this is encouraging because it's a low pass frequency. It's a low pass filter, so that means at low frequencies the signal is going to pass through and come out the other side as it was before. So part F, we're going to look at high frequency. This time we're going to make the assumption that omega tends to infinity, so in our complex voltage transfer function we replace omega with infinity, and that's what I've done here. So what have I done? I've said next step is this 1 is equal to 1 at an angle of 0 degrees. I've converted it to polar form, and here we've got infinity divided by omega naught. This is infinity. Infinity divided by anything is still infinity. So we have 1 plus j infinity, and because the infinity term is so much bigger than this 1, we can ignore it. So we can just say this is j infinity alone. So it's just j infinity, which if we convert to polar form is infinity at an angle of 90 degrees. So next up we do this phasor division, and we get an answer of 0 at an angle of minus 90 degrees. So we need to separate the magnitude from the phase, and that's what I've just done in this statement here. So what we can say is the amplitude response is 0. It's attenuated, so the signal comes in and nothing or close to nothing will come out again. And the phase response is minus 90 degrees, so there's phase distortion. So at high frequency our signal enters and a very altered form of it exits our filter. So let's look at our interesting condition at the cutoff frequency. This time omega is equal to omega naught. So in my equation I've replaced omega with omega naught. So what we can see here is that this simplifies quite easily. So we end up with 1 at an angle of 0 degrees over 1 plus 1j. This is in rectangular form. We need to convert that into polar form, and that's what I've done in the next step. So if you put this number into your calculator, you should get this answer out again. So we can just do this polar division. So it's 1 at an angle of 0 degrees over 1.41 at an angle of 45 degrees, which gives us an answer of 0.707 at an angle of minus 45 degrees. So that's the magnitude and the phase response at the cutoff frequency. So let's summarise that. The amplitude response is 0.707, so there's a small amount of attenuation, and the phase response is minus 45 degrees, and this is at the cutoff frequency, so there is some distortion. So now we've done those three steps, part H asks us to plot a straight line Bode plot for the filter. So let's do that now. So what I've done is, with our Bode plot as ever, we've got two parts. We've got the amplitude and we've got the phase. So let's look at what we need to do for the amplitude. Well, we need to know what the value of omega naught is, and we calculated that in part B. That's 6,250 radians per second. What we need to do then is plot from low frequency to omega naught as a straight line at the low frequency gain, so that's going to be at 0 decibels because there's no attenuation. Then we need to roll off the gain from the cutoff frequency, which is omega naught, at minus 20 decibels per decade for every 10 omega naught as a straight line. This is the same thing as we did in the lecture, so we went into a bit more detail in that in your lecture notes, so have a look there. So that's how we plot the amplitude for the phase. We're really interested in 3 frequency points. We're interested in 0.1 omega naught because we assume this is the low frequency response. We're interested in omega naught, which is the cutoff frequency, and we're interested in 10 omega naught, which we assume is the high frequency response. So at low frequency, which is represented by 0.1 omega naught, we know the low frequency phase shift is 0 degrees, so that's the point we plot on our Bode plot. And then at high frequency, which we assume is 10 omega naught, we plot the high frequency phase shift, which in this case is minus 90 degrees. That's what we calculated. And then at omega naught, we just need to check that the phase shift is minus 45 degrees. So we need to draw a straight line between these 3 points. So let's have a look at how that looks. Let's rotate. So what have I done? Well, I've started off by saying what I'm plotting. This is a Bode plot for a low-pass filter for problem sheet 6, question 2. And omega naught in this case is 6,250 radians per second. So I've plotted omega naught in approximately the centre of my graph paper. Then in the next decade I've marked 10 omega naught, and at the next decade down I've marked 0.1 omega naught. These are our important frequency points. We've got the frequency in omega increasing in this direction, and we've said that I'm plotting the amplitude h to omega along this axis, and I've got 0 dB, which is our non-attenuation. Then I've got minus 20 dB and minus 40 dB, because we know we're going to roll off at 20 decibels per decade. So that's why I've chosen those values. So we need to mark omega naught on our graph, which I've done here. Because it's a low pass filter, we just draw a straight line to represent the low frequency gain, which goes from 0, low frequency, all the way up to our cutoff frequency here. After this point, we need to start to roll off. So by 10 omega naught, we should be down minus 20 dB. So I marked that point here. And at the next decade, we need to be down another 20 dB. So I've marked that here. So now I've got these 3 points marked, I can draw a line to connect them. And that's what I've done there. And that's it for the amplitude response. So now we can draw the phase response. Once again, I've got omega naught marked, and I've got 0.1 omega naught, which is the low frequency value, and 10 omega naught, which is the high frequency value. And these are each separated by a decade on the graph paper. So the graph paper needs to go from 1 to 10 to be a decade, and it's linear in this direction. So this is 4-cycle lin log paper. So let's plot the low frequency values. At low frequency, which we assume to be 0.1 omega naught, the phase response is 0 degrees, so I just draw a dot there. At high frequency, which is 10 omega naught, we calculated the phase shift to be minus 90 degrees, so I've drawn that here. Then I draw a line to connect these 2 points, and I just check that omega naught falls at approximately minus 45 degrees, which it does. So that's the first bit. The next part, just to finish this off, I need to join up from the low frequency phase shift just straight back to the edge of the graph, so that represents the low frequency phase shift, and at this end I need to go from the high frequency phase shift and extend that line forwards, so that's the high frequency shift. So what that's saying is at low frequencies there's going to be 0 phase shift, and then once you hit 0.1 omega naught there's this transition zone which extends up to high frequency, which is 10 omega naught, and after 10 omega naught we enter the high frequency range where this is all attenuated by it's all shifted by minus 90 degrees. So that's how you answer question 2, and that's how you draw the Bode plot for it.